Where's Clayton?
Still making edits?
Necessary.
Tommy, can you guys see this? Do we have the lights down? Do we have the lights down? Audience.
Probably.
Thank you.
Put the Jesus light on.
Jesus light.
I'm by yourself.
Well, there you go.
Okay.
Job.
Alright, exercise, make sure that your leaders are split halfway.
Please stop, you're a child.
And then Justin. Alright guys, 10 minutes on the clock, let's go.
Okay. Ionization energy. Ionization energy is the energy required to form an ion. So take away one electron. It's always endothermic because you always need to put in energy to take an electron out. Also known as binding energy.
So what kind of ion?
Cation.
Thank you.
So so there are multiple kinds of ionization energy. The first one is the amount of energy that's required to remove the outermost electron from the initial atom. And we have a couple of examples, and magnesium has a larger ionization energy because it has 2 electrons in the outermost shell, while sodium only has 1.
And because it has more protons, so it has a stronger ZEF, as the electrons are being pulled closer to the nucleus of that.
Alright, so next what it said is that do not say that it says more electrons has nothing to do with the size of the ionization energy. In this case, the first ionization energy is purely based on what?
ZEF.
So tell me how many protons you use out.
Magnesium has
17?
sodium.
12?
12.
And
And
sodium has 11.
so what does that mean?
Nuclear charge. How strong the electrons are being pulled in the nucleus.
Is that when you're ready to go, guys?
Okay, second and third ionization energy. These are what it takes to further remove an ion. When there's multiple ionizations, the IE increases greatly because of the repulsion of the electrons in the shells. And once an ion has reached full shell of valence electrons, it requires far more energy to separate. And the number of electrons, or the number of valence electrons, is determined by which family it is in, an exception of transition metals.
Can you, so multiple ionization energy is causing ionization energy to increase greatly. That next part, not necessarily the reason why.
Okay, because once you've lost the first electrons, the remaining electrons are pulled in closer because of the charge difference.
So because that effectively is stronger.
Yeah, proportionally. So it's harder to get the electrons out.
Because electron function would actually be favorable to alleviate the energy. They would want to go away. They would want to be shaken. There's a lot of electron pushing. The lack of one electron actually limits the electron function, leaving the nucleus to be actually effectively stronger, which is why you guys talk to us able to.
Okay, well, see, as magnesium breaks apart and ionizes, the first ionization is what we talked about, 738. That has to do with just the initial, with the protons and how it breaks off. And then the second ionization energy is going to require a lot more energy because now the electrons are going to be closer to the proton and it's going to pull harder, and then it gets even closer and even closer. And it's
700 or about doubling, right?
yeah.
It jumps greatly because you've gone from the energy level, the third energy level, to the second energy level, making it have the same amount of electrons as helium, but there's still more protons. Neon. But there's still more protons that are pulling it in closer due to the effective nuclear charge.
I just want to add a term to this. This is with ionization energy. Let me ask. It is most important one. It is most commonly seen right out, and then atomic radius right after that. The jump from 1400 to 7,000. That is a significant jump. So if I did not say that with magnesium, you should be able to tell us based on data how many valence electrons this unknown atom has. So if you see a huge jump between them, you can assume that third, for example, this third ionization energy is taking something called a core electron versus a valence electron. That's a good term to use when you're trying to explain how you know that this particular element has has two valence electrons because the third ionization energy is so significant, it's pulling it in core electrons.
And you can see that from here to here in sodium too. Here to here in magnesium. Aluminum.
Yeah, so you go from like 500 to almost 5,000, and then let's see, like 2,700 to almost 12,000. So it's very significant. So we do pay attention. They ask data questions like this all the time. Yeah.
Okay, the general trend is this one goes left to right across the group and up the left to right across the period up the group. And as you go left to right, the atoms get more protons, so they have a higher nuclear effective charge, pulling the electrons closer, which requires more energy to break them apart. And then as you move down each group from top to bottom, the ionization energy goes down because there's more shells of electrons, so they're farther from the nucleus. There's more shielding in between them, so it requires less energy to pull them apart.
So there's less interaction between the nucleus and the valence shell that are bigger. Another term for that.
Electron shielding,
So electron shielding or less what attraction?
Coulombic attraction.
Because of the distance factor. Thumbs up on your videos.
And this one just shows it more where it's going, increasing as it goes up and increasing as it goes right. And from this, you can easily see that. Oops. And this one, yeah, you can go. Okay. And that one's just a 3D model where you can see that the noble gases and the halogens are all pretty large. And then as you move farther right, farther left, and farther down, you eventually get to very small amounts of ionization energy required to pull away the atoms. Click it in. And this one shows it just some more. And there are also a few exceptions when you're going from group 6 to group 5 and group 3 to 2. And we'll get more into that a little bit later on why it goes up instead of down.
Yeah, ionization energy and atomic radius. That's the ionization energy. The trend of ionization energy is the opposite of atomic radius because ionization energy is directly related to the force of attraction, which is inversely proportional to the distance between the proton and electron. So basically, as atomic radius gets larger, then the ionization energy becomes less due to what we talked about earlier with Coulombic forces and shielding.
The energy levels, how they relate to ionization energy, basically more energy levels, ionization energy is lower because there's less Coulombic attraction between the electrons and the nucleus since they're farther apart. Good to go.
And then your last statement there is that decreases with more energy levels. That is not a true statement. That does not have to do, never relates death and energy level. You're relating the shielding energy level and death to what?
Protons versus electrons.
Right. You can state there's less attraction, or the attraction decreases with more energy level, but it's not the death. The terminology is very specific. It's not being hard for you. Wait, so Zeph is what? Zeph is related to number of protons across a period, meaning the same energy level. So increased protons increases Zeph. Zeph is going very specific to the with more energy levels, you have something different. You have more electron shielding, which is
Okay, so there are a few exceptions to the trend. Like you showed earlier on the graph, there's from 3A to 2A and 6A to 5A. 3A to 5 or 6A to 5A is explained through acknowledging a sublevel change, and then from 6A to 5A, a full sublevel is broken, which also uses more energy than is typically needed. And this occurs because of the way the electrons are formed in their orbitals and then how they're removed and added to become ions. And I can draw a picture to help you understand. Erase all of it.
Yeah.
You can understand. Okay, so boron and beryllium. Okay.
We do electron configuration 1s2, 2s2.
And that's what boron is. And then to make it ionized, or an ion, you have to remove this electron. So, so that one's taken away, making it boron ion. And then that's from boron to beryllium. So I'm going to draw beryllium. And then beryllium ion.
Right, 1s2.
Yeah, and then that one. So the ion, you'd have to remove one. One of them. So that would make it like this. And the boron is gonna require less energy because you're just removing it from this orbital here. But since this one, the p orbital. So, but since this one's in the s orbital, it requires a lot more energy to remove because it's electron shield.
Because it's in the S block, which is closer to the protons.
What is the term for S block?
Zen.
So, Columbia.
What is the word that we don't say?
Oh, electron penetration.
Nuclear
Nuclear
penetration.
penetration.
Okay, so please write this down. This can also be on the slide. Everybody make sure, if you don't draw this, at least you can melt down the electron configuration. Boron 1s2, 2s2, P1, P sublevel is farther away from the nucleus slightly, meaning it does not undergo nuclear penetration. I'm screaming this for me. And then back up for me, Jack. So that's why boron has a lower ionization energy, despite the fact that it has higher number of protons, meaning more Z to the right across the period. Beryllium has a higher first ionization energy because it does not have p electrons, meaning it must take an s electron, which is undergoing nuclear penetration, meaning it's more attracted to the nucleus. So it's a bigger fight for that electron via ionization energy. Don't think that a bigger problem they can say nuclear penetration. Impressive. Tell us more about 5A to 6A, and then I'll stop.
Could you go back to the graph? So from 5A to 6A is
So it should increase,
Green
right?
to the blue.
yeah.
The green one is high, the blue one is low. Tell us why.
I'm not.
So when you have so when the P block is filled with one, can I do a marker? Yeah. So when you have the P block where it's like that, and that's what it looks like in the sixth group.
Here's that
that would be oxygen. And so you have so you have these four words, where this one is the only one with an extra electron, and the repulsion is, so you have an electron repulsion between these two electrons, and when you're ionizing it, you're removing the repulsion between the two, causing them all to be equal, and there is no repulsion, allowing the energy level to pull closer to the proton.
So why does it?
Because the electron repulsion is pushing the outer energy level farther away from the nucleus.
Well, oxygen has more. So if you're comparing oxygen to nitrogen, how much have the borons are?
So in nitrogen, it's going to be that. And then you have to remove one of those, like this. So it's going to require more energy than it would require for oxygen to ionize.
Oxygen, which to me seems like it would take more energy, right? So here's the point: the electron-electron repulsion is more favorable to get rid of, despite the fact that oxygen has one more proton, there's no force set. So the electron-electron repulsion is more stabilized. I'm sorry, if you get rid of the electron-electron repulsion, it's more stabilizing. That's why it takes less energy to remove that fourth electron from P block. For oxygen, that's why it takes less energy to remove that one than the third electron from P block for nitrogen. There is no electron repulsion for nitrogen, so there is no extra stability gain by removing it, so it's more of a Z spectrum.
It's going to be more stable, and this one's going to be less when you move it.
Right.
That's what she's trying to say.
That's going to every 5A to 6A cell, and every 2A to 3A cell.
Nope.
Everyone there, okay, you guys all understand. And then use this so that we can see what you're talking about. Where's my mouse? Alright, we're gonna do a lot more explanation of
Okay, it's Chinese and Custer.
okay.
Okay. This the sensitivity graph, like it increased from like top from left to right, and this increased from top to bottom. And electron activity is a measure of tendency of atom to detect one electron, and the union for it is kilojoule per mole.
Real quick, you say bonding electrons. So what kind of bond are we talking about? Probably covalent bond. This is a bonding situation, actually, for external bonds. Important stuff.
Okay, so there's a couple. Oh, yeah.
Okay. Some traits are that a step increase the attraction between the nucleus and electron increase the electron activity, and as the number of energy level increase, nucleus has less of attraction to its outmost electron.
This is that.
That's a simple.
Yeah, that's everything. Literally every trend exists because of those two factors, that the energy levels and the electron shell. So that's not new to us. Everybody knows explaining that. Like everybody should be aware of which trend is
Yes. Is everybody good? Here are the more specific factors that affect it. First is the distance between the protons and electrons. So as the distance between them increase, the force is going to rapidly decrease.
And you can figure this out by taking the distance. Let's say it increases by 2, by a factor of 2, so it's doubled. You'd square that, and that's how much the force or electronegativity decreases by. So that means it would decrease by a factor of 4, which is 1/4 of what it was. Another example is like if you quadruple it, you'd square 4, and it'd be 1/16 of what it originally was. Next is the total charge of the element. So as the proton increases, this is only talking about going down a group. As the proton increases, the nucleus size will increase, or I'll say the same, but the size of the atom will increase, which will gradually decrease electronegativity as you go. So you can see like these. So you can see like as you go down the group, it's going to gradually decrease like all the way across. If you're talking about periods only, it increases because the Zeph energy increases, which is going to create a more positive charge because there'll be more protons. When there's more positive charge, the atom's going to get smaller, and it's going to also attract more electrons because of that.
Right, Pauling scale has a top value of 4.0, bottom value 0 technically, but
Well, that's the exception. And also going down is the shielding effect. So as you go down a group, there'll be more energy levels, and as there's more energy levels, the valence electrons can't attract any more electrons because you know that negative and positive attract each other, but when there's negative and negative together, they only the repulsion, so they won't attract any more electrons because of that. And then lastly, as it gets more complex, like the atom itself, the shielding effect also goes into play, and that'll also decrease electronegativity if you talk about like how it gets more complex with the shape.
I'm going to add on top of the fourth one, the complex orbitals we talked about are probably the F block orbitals. So the more orbitals you have in the inner core, which is the inner core electrons, they shield all of the positive attraction. That's why there's that complexity associated with like transitionals.
And to kind of go off with what Summer was saying about F block. Oh. Oh. Oh, so to kind of go off what Miss Enlow was saying about how F orbitals are very complex and it makes it harder to be electronegative. When you look at our graph, which I'll show everybody when we're done, there are no values for the lanthanides or actinides because their structure is so complex that they just can't have values. As you can see, there's no values for any of the lanthanides or actinides or pretty much anything beyond, I think that's radium, which is also called lanthanide contraction. Everybody good? Okay. And so the other exception is noble gases. See, the reason why noble gases don't have a value for electronegativity is because they have a complete set of valence electrons in their outer shell, which means that they don't need to take any on,
there are two noble gases that have values, which I believe is xenon and krypton or radon. You know, it's krypton, yeah. They have a value just because they're so large that they can take on another electron. They don't need to though, which is why their value is very small. So essentially, because they have an outer electron, they have a full outer valence shell of electrons. They don't have a value because they don't need.
Because they're an octet, and once you're an octet, you have no need for further electrons. But if you're like about to like a halide, and you're about to go to octet, you're gonna have like a strong need for electron. But also, if you're like sodium, you're so far away that you don't really like need electron. That's why the value's lower.
Why is the value lower? It's not because they're needing for electrons. They don't feel them.
You're like,
What's causing value lower?
so lows that.
Lows up. And then why is, like, for example, halogen going to have a higher
Because it's going to have a very high Z.
right? Relay back to that.
Yes. All right. That's it.
Could you go back to the 3D graph? I just want to see like the
And I want to ask you a question. You have this lovely picture on your handout with a polar covalent, non-polar covalent, and ionic bond. How does that play into your trend? It's a good picture, and it means something because this is our related bonding.
Well, that's because
So,
it's non-polar.
what is non-polar?
It's not polar.
Very good. Can you go back to the graphic there? Let's see the three values on it. Okay. For example, if I'm lithium, if I'm lithium, and I approach fluorine, what kind of bond am I going to form?
Ionic.
Because negative and positive.
It's a
No,
metal
it's not
non-metal.
negative positive.
It's a metal non-metal.
It's what?
It's metal and non-metal.
Yes, but there's, I want you to explain Kind of. Okay, fluorine has a high electronegativity. It has a high energy associated with the desire for electrons. Lithium has low. So what's lithium going to do?
It's just going to give it the other electron.
Give it away. It's going to give it fluorine. Okay, so that's going to be ionic, like you said. That's a literal donation of an electron. Let's say nitrogen and oxygen. What are they going to do?
That's going to be a covalent bond.
Right?
Because they're going to share the electron.
Right, but are they going to share equally?
No,
Yeah.
oxygen's going to have it a little bit more because it has a higher electron.
So would that be polar or not polar?
That would be polar.
Polar means right, yes, here. Oxygen and nitrogen are probably going to be polar. Who would yield a non-polar covalent bond?
Something like this sulfur and that carbon right there.
Carbon disulfide. Great. Give me something else.
Also, you know, that good old nitrogen and chlorine. That's yeah, diatomic stuff.
Thank you.
Yeah.
So anything diatomic because it's bonding to itself, there is no difference of electronegativity, so they have to share equally because nobody wins. Fantastic. That leads us to our last group.
And you are. No pressure. I know. Like, I expect you to have some background knowledge about what you're teaching.
So we know what you're talking about.
One of them is the detonator.
Well, I blew something up, oh well. Melting point and boiling point. Mainly melting point. Okay. So the general trend by group is
It decreases in boiling. It decreases in melting point as you go down the curve, but there are a lot of exceptions. For example, carbon, which is extremely high, which we'll talk about later.
Yeah, because theirs look like a technical trend. Like,
It's more of a generalization.
but they have a lot of factors. So you need to make sure you're aware. Because they're more about properties of chemicals and their elements of nature. They're gonna give you a lot. They're leading us into bonding.
Attraction, not bonding.
Attraction.
Attraction. Okay. Okay. Melting point is the amount of energy required to overcome IMFs to change the solid phase of a substance to a liquid. And boiling point is the amount of energy required to overcome IMFs and change it to liquid to gas. Intermolecular forces. So the attraction's holding, yeah, hydrogen. It's not, it means attraction.
Okay, so one generalization is that most metals have higher melting points while non-metals have lower melting points, and this is because metals are usually found to be in a solid state at room temperature, and non-metals are in a gaseous state. So in a solid state, the molecules are closer together, which has a stronger attraction, and the stronger attraction has a higher melting point. And so non-metals have a weaker attraction because the molecules are farther apart, and so it has a lower boiling point.
Carbon possesses the highest melting point because out of all the elements, and helium possesses the lowest melting point. Out of the halogens, melting point and boiling point both increase down the column generally, and noble gases, boiling point and melting point will increase down the column. They have very low boiling points.
For the carbon is literally never by itself. Can you tell us why? Or tell us why?
That's coming up.
So here's the periodic table to show like how you can see the non-metals have lower boiling points and melting points, and the metals have higher.
Which we're getting to.
And on the slide, comment later on, you describe the halogens.
We described the column, or the
Remind me to back that.
Okay.
So for each period, the melting point starts out very low, and then it increases across the period, and then decreases by the end of the period. And this is because of the transition metals in the middle have higher melting points for the reason I said before. And then the non-metals having the lower melting points. So that's the general trend across the period. And then going down a group, the atomic radius decreases, or
Increase.
increases.
Increase.
Yeah, the atomic radius increases, so there's more room for molecules to spread out, which, or no.
All right.
It's,
You gotta be with me on something. Now let's be with me.
Okay.
Okay, so why did you stitch together?
because there's a strong attraction.
But why?
Has a smaller atomic radius.
Smaller atomic radius, meaning the nuclei and the electron clouds are close together. You see them? Okay. What happened?
The atomic radius.
It's got bigger.
Okay, so that's the level of attraction.
Decreases, which decreases the melting point, which requires less energy to separate. Okay.
And this is just a visual of the periods and how they increase in the middle and then decrease once you get to the melting point.
On that graph, we talk about what happens as you get to hydrogen when you get back here.
So we peak at carbon, and then once you get to like nitrogen, oxygen, fluorine, because they're in a gas state at room temperature, your bond to separate the attraction forces, it requires less energy. So
And you see that they're little tiny clumps beneath the zeros?
yeah,
So
so
that means that their boiling point and melting point are negative
is
values.
yeah.
So do we really ever see
You'll never see them in a melting point unless you're
like
for some of them,
total temperature?
yeah.
Right.
So the more attraction an atom has, the more energy it takes to overcome the attraction. So this increases the melting point. And melting points are varied, so there's not really a specific general trend across the entire periodic table. But you can draw certain conclusions. So, like we said earlier, nonmetals have low melting points, but we also said that carbon has the highest melting point. And that's because it's always bonded to 4 other atoms, which means you need more energy to overcome all 4 bonds. And also earlier we said that the melting points for atoms of nitrogen, oxygen, and fluorine, there's such a sharp drop in the melting point because after carbon, those elements pair up to form diatomic molecules, and even though the covalent bonds between the atoms are strong, the IMFs are weak.
So can you tell us what carbon forms that form those 4 bonds that maybe some people are aware of, those common forms of carbon?
And allotrope,
The allotropes of carbon are
graphite, and then diamond.
and graphene. They are humongous structures. They have millions of bonds. They mentioned earlier called network covalent bonds or structures. That is the only reason carbon has this anomaly. It's simply because it makes a humongous structure. It has nothing to do with that. And then their London dispersion forces is a very weak force. However, they mentioned this for us and say, way down the group, fluorine, iodine. Fluorine has a lower melting point than iodine, and one would think that iodine being bigger versus fluorine being smaller, the trend would be opposite, but it's because of the something called polarizability that these ions have. And we're going to get to that later. Polarizability is a term that describes why that occurs.
That's it.
Okay, we
Can you
can
go back
real
a slide?
fast.
Yeah.
Okay, if you are done with this, please pull that graph we started last week. Thanks, guys. All right. So the
Small heart attack I had this morning. I think we've done our duty. Everybody knows what we're talking about, huh? Oh, I was trying to get people to fix their stuff. Okay, this is the graph that you have. Is this radiac? Sorry, hold on. Ionization energy. You have something similar to this. You might have to explain on my test what and so if you don't have this graph all the way, I want you to at least make note of the 2 exceptions, and this is what Lewis's group was talking about earlier. Lewis, I have one for you, but just the whole thing. And so, yeah, he already has his opinion. So we go from ionization energy. This is going across a period, okay? So as we get to lithium, you expect the ionization energy to increase as you get to beryllium, and it does. But then, like I think Jack was saying this one, boron to beryllium, you expect there to be an increase because the trend says it increases, but it does not. Why? Why does it not increase? But we have some terminology for this, right? All right, so the exception occurs there. So I'm going to say B, or boron to beryllium, right, the other way. Did I write that wrong? I did, okay. From beryllium to boron. That exception occurs because of nuclear penetration of the S sublevel. And so Beryllium is going to have technically a lower ionization energy because it actually has a p level electron that's easily attained because it's not undergoing nuclear penetration. So we've explained that anomaly, and then we increase to carbon and increase, like the trend says, to nitrogen, and then we drop and we get to oxygen. Why is that again? So who has electron repulsion? Oxygen, because it has how many electrons in P? 4. It has a 4th electron in the P sublevel, which creates electron-electron repulsion, leaving it easier to take because it leaves the atom more stable, versus nitrogen, which is ending at 2p3, and oxygen ending at 2p4. And so the 2p3 electron, it has no electron repulsion, so it has the general trend occurring where it increases in energy from carbon to nitrogen. So a half-filled sublevel is technically more stable than a 4th electron in a sublevel. And so then you normally increase to fluorine and neon like normal, but then the exception occurs again and again. So the same exact reasoning, so nuclear penetration between group 2A and group 3A, and electron-electron repulsion between group 5A and 6A occurs periodically, because that's why it's called the periodic table. Okay? That's literally why it's called the periodic table. I didn't make it up. No. So this is between 2A and 3A, and then this other one is between group 5A and 6A. Whew. Okay. So we have about 15-ish minutes left. We have all the trends we need. Tomorrow we're going over photoelectron spectroscopy, which relates to some of these trends, the reasoning and everything about electron configurations, orbital diagrams. It's more graphical analysis. But right now I'm taking number 1 through 30. So multiple choice 1 through 30. That's what I want to do right now. We're going to check them tomorrow. Please have them done. There are 90 on this multiple choice. So we're doing the rest of them tomorrow or the next day. Okay? So those of you who had some free time this morning, be sure to be ahead. So I'm expecting that. I'm going to draw some pictures of them, okay? Give me a second. So 1 through 30. Go team.